So today's topic is Hamiltonian graphs, and it is uh, maybe a little bit more. So one hand side it's a little simpler than Euler graphs, and other hand it will be a little more complex. So the easiest part is that we don't need this uh, difference between circuit and cycle because it will be the same. So we called uh, again if usually when we talk about edges we can also talk about vertices because they're in some sense dual to each other. So we called I remind you that we call an order. So we have that we called the graph G has an Euler circuit if we can if there is a so if it is the circuit of the graph considering all edges, and we call the graph G is Hamiltonian or has a Hamiltonian cycle if it has cycle that contains all the vertices of our graph G. If there is a cycle that containing all the vertices of G. So we don't need to move through every edge, but we need to move through all the vertices. And of course, so we consider is a cycle, so we don't want to move, so we don't want to visit the same vertices two or more times. So we need to meet every vertices exactly one time. So we want to find a cycle in our graph. Of course, for some graphs, it is easy to find the Hamiltonian. So, for example, if you have like one cycle, it's Hamiltonian graph. And of course, if you consider full graph Kn, for example, K5, it is also Hamiltonian, and we can find different Hamiltonian cycles here. So, for example, we can go like this, or can go like this, and this will be all Hamiltonian cycles. But also, for example, if you have a tree, it is of course not Hamiltonian because it have no cycles at all. And similar definition, we called that we have a Hamiltonian trail or Hamiltonian path if we have a path containing all the vertices. If there is a path containing all the vertices of G. So, for example, if you have the easiest example is just the path. Of course, if we have a Hamiltonian graph, it will have Hamiltonian path because we can just take the cycle and throw out the one edge of the cycle. It has Hamiltonian path, but not Hamiltonian. And if G is Hamiltonian, then G has a Hamiltonian path. So it is maybe more simple to understand the notion of Hamiltonian cycle, but the hardest way is that we have no criterion for graph G to be Hamiltonian. For the Euler graph, we just can uh, look at the degrees of all the vertices, and if G is connected and all the vertices have the even degrees, then G has an Euler circuit. But now we don't have any such criterion. We have only sufficient condition, uh, or maybe uh, so maybe other conditions, but we don't have any criterion. So if and only if and only if rule. So I maybe first we will look at some examples, and then I will prove some theorems of when we can guarantee that graph is Hamiltonian. So maybe I will give you some examples so you can see if we have or not have a Hamiltonian cycle in this graph. So we can start from graph K33 that we made before. Full bipartite graph, or maybe these graphs or maybe we can ask myself, so you can ask yourself, is graph KMN, so full bipartite graph, when the first part has m vertices and the second part has n vertices, and we take all edges from first part to second part. So is this graph Hamiltonian, and for which m and n this graph is Hamiltonian? The second example will be so-called Peterson graph. I don't know if you previously made this graph on the first course.
Yes, sir.
So it has 10 vertices, and we can like draw this picture. So we have like star and pentagonal, and again we can ask yourself if this graph is Hamiltonian. Maybe
Sir, so
yeah,
if the graph has Hamiltonian path or Hamiltonian cycle, it's a Hamiltonian graph.
we call the graph Hamiltonian if it has cycle. We need to find the cycle.
Okay.
So if there exists a Hamiltonian cycle? Okay, maybe so you can thought about these two pictures, and maybe I will find some.
Sir, for Peterson's graph,
Yes.
I think Peterson's graph is Hamiltonian, sir.
Why? So can you explain how to build this cycle?
So first we can go through all the vertices on the outside, then go through the last vertex. We use the edge that connects to the star. Then we can just visit all the edges in the star.
Yeah, but if you do that,
Visit all the vertices and stuff.
so you can go like this, and then you can go like this.
No, so we go back to the
So if you want to return
can't
to
we
some,
go
yes,
can't we go to the vertex we started from?
but they will do not a cycle, because cycle must consist only each vertex only once. So we cannot go like this. So we cannot just go through the circle and then move here, because so we can try to build this thing, but we will not obtain the cycle.
Sir, you said K5 is a Hamiltonian cycle, right?
Yes, in K5, we can just we can have only 5 vertices, so we can just uh, build a cycle here. It contains only all the vertices, and we meet each vertex only once. And of course, so each kn contains just so if we have all the edges that we can take the edges 1 to 2, 2 to 3, between 3 and 4, and so on. And so it will build a cycle. But here we of course we can build a cycle on the inner verse or outer verse, but we need to connect with them. And this is a problem. How do we do it? Because if we just try to so we start here, like we can try to build like some complicated path, but so here I constructed a path, a Hamiltonian path. It connected all the vertices, but it's not a Hamiltonian cycle because my endings of this path are not connected to each other. So I cannot build a cycle from this path. So maybe I will give you another picture. It's just similar to Petersson graph, but we have like additional, but maybe have some other links between the vertices. Yeah, maybe I could just redraw it to be picture. Okay, I think I will give you like 5 more minutes and then we can discuss it. So
Okay, sir.
just wait here. Okay, so do you maybe have an idea for some?
Sir, for the first one you drew,
Yeah.
I can't find the Hamiltonian cycle there.
Okay. How?
I can't find one.
You can't find. So for the case
Yes.
3, maybe.
So for K33, you just can draw the lines to all the vertices, like a circle, like a square, right?
Yeah. Sorry. Maybe I will. When I wrote case 3, I forget to wrote like 2 edges. So you need to connect all 3 to the other 3. So you have all edges between
Oh,
this
okay,
3 and
sir.
this, and this 3 and this 3.
Because, oh, I didn't know it was K3 because I can only see 7 edges.
Yeah, it will be. It should be 9 edges between them. Yeah, I will just need to start share again.
I'm sure I can't see anything.
Yeah. I understand.
It's
Just
loading.
Okay.
yeah.
Sir, if it's a K33 graph, then I think it definitely has Hamiltonian cycle.
Yeah, of course, because you could just like try and find something. You start here, like you go through here, then here, and here. So you just go to the other part and then return to the new vertex and so on. And so it's similarly can be found that, so we can prove that every graph like KMM is Hamiltonian because you just go to the other part and then go to the new vertex and so on. So you can just start here, then go like this one. But if there is different number of parts, then you can't build a cycle because cycles. So if you have a cycle, then we have even vertices there, and then half of the vertices must be from the first part, and the other half must be from the second part. But we cannot do that if m is not equal to n, so it will be not Hamiltonian. So if you look at the Peterson graph, again, it maybe not very easy to see. So it's maybe not such obvious that how to look at this graph. So I can give you I could try to give you like 2 or 3 proofs about this graph. So first of all, suppose we have a cycle here. So we suppose this graph is Hamiltonian, and we can build a cycle. Then we can denote, so we can color our vertices into 2 different colors in a correct coloring, such that the vertices of different colors doesn't need to be adjusted. So just alternating coloring of this vertices, exactly that vertices here. So suppose we have a cycle and we just try to find this coloring on the Peterson graph. So suppose we have a cycle, then we have a coloring on Peterson graph such that these colors will be, so these points are somewhere here. But if we look, so for example, we can try and see that. So this will be like blue one, and then if we have some edge in the graph, then for example, this will be orange, and so on. So suppose we have a Hamiltonian cycle. I want to look at the number of colors that I met here in my graph. So is it true that if I have a cycle, then there will be at least two vertices of one color that connected to each other, or no, in Peterson graph?
Yes, sir.
Why is it so?
Because in the end, when you connect it, you're gonna connect the same colors, I think.
So you only want to use two colors?
Yes.
It's gonna have adjacent vertices with the same coloring because the number of vertices are odd. So we can have.
So since Peterson graph is not a bipartite graph, then there will be two vertices of the same color that are connected to each other. Okay. So
But I think you can have a vertex with different colors also.
yeah, of course, but I need to start with the vertices which have the same color. So you know that Peterson graph can be two colored, so it's not a bipartite. Then there exist two vertices of the same color that are connected to each other. Two vertices of the same color connected to each other. They are adjacent to each other, connected to each other. Just right here. Adjacent, sorry, if I can. Adjacent, sorry. Okay, so if we start, so suppose we have two vertices of the same color, then we know the colors of this their neighbors. So for example, we need this and this to be orange, and also we need this and this to be orange, because it is the unique neighbors and we have them in a cycle. And again, for if you look, for example, in these vertices, all of these neighbors are blue, all of these neighbors are orange, so it should be orange. And all of these neighbors are orange, then it should be blue. This all this so here we'll have like maybe, yeah. So here we'll have a contradiction, because so for this vertex, so if I look at this vertex, it should be blue, because if I have three edges and one of them blue and two of them orange, that it should be blue, because if I have a cycle, I need to go into the vertex and out of the vertex. So if I have two vertices of the same colors and one of the different colors, then I need this vertex to be blue. And also this vertex should be blue because I cannot have, if I have this orange, that I cannot come from this vertex and go to another vertex. So this also should be blue. Do you understand this or not? So uh, if I have vertex of degree 3 and we have like two orange vertices and one blue, then my vertex might also be blue because my Hamiltonian cycle must go through this vertex, and it can be only going if these vertices are the same color, because I cannot go from the blue and go for the blue. Okay, so this vertex must have blue color. And so if I'm coloring, I see that I have exactly six vertices of blue color and 4 orange, and this is a contradiction because I need to have 5 and 5. Okay? Or we,
Yes, sir.
yeah. Maybe it was a little bit hard, but I can just try to try to give you another solution how to prove that this graph is not Hamiltonian. So suppose it is Hamiltonian. So we have a cycle. Let's draw the cycle. So for example, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 vertices. 10 vertices here. And I have 15 edges in my Peterson graph. So I have 5 edges elsewhere. So I need, if I have a Hamiltonian cycle, I need to add five more edges that I have in my graph. I'll start from any vertex. For example, I start with vertex number 1. Where can we these 5 edges? So if we have edge going through the 1, and of course each vertex has degree 3, so each vertex must have additional edge. So we have an edge starting at 1. Where can we finish? Can we finish this at 3 or 4, for example? So can we go here and here? Can this edge connect 1, 3 and or 1, 4?
Yes, sir. I think so.
Why? Can we? So if we have 1, 4, then we have a cycle of length 4 in our graph. Do we have a cycle of length 4 in our graph? Peterson graph.
No.
Yeah, of course, it's easy to see that the minimal number of vertices in cycle is 5, because we don't have a triangle,
Yes.
and we don't have a cycles of length 4 in our graph. So we cannot connect 1 with 3 and 4, because otherwise we will have a cycle of length 3 or length 4, so triangle or cycle of length 4. And of course we cannot connect it through the 8 or through the 9, because we cannot have a cycle of lengths 3 and 4 either. So it should be connected with one of the vertices. So it must be connected with the vertices like 7, 11, like 7, 6, or 5. So we need to, so we need to look at, so I just draw this out. So if we want to connect one with something, it should be 5, 6, or 7. So for example, 5 and 7 are symmetry to each other. So we can just look at the 5 or 7. So we have like 2 pictures. We can connect it one through the 6 or one through the 5. If we connected 1 through the 5, we'll look at the vertex number 10. And for the same reason, it should be connected only with vertices like 4, 5, and 6. And each of this cannot be happening because if we have 10, 4, then we have a cycle of length 4 here, which we don't have. If it is connected with 5, then we will have simply a triangle here. And if it's connected with vertex 6, then again we will have a cycle of length 4. Yeah. So we cannot connect 1 and 5, and for the same reason we can connect 1 and 7 because we can look at what vertices are connected with 2 and so give a contradiction. So all we need to prove that 1 cannot be connected with 6. But of course, but again, we can just look at the what. So so here we can connect it like 10 must be connected with. So 1 is connected with 4, 5, 6, and 7, and 10 is connected with 2, 5, 6. So 10 must be connected. So cannot be connected. Here we have a triangle. Here we have a cycle of length 4. So the unique possible solution here is 10 is connected to 4. And for the same reason, 2 is connected to the 8. But then, for example, if we look to the vertex 3, then it can be connected with 9 because we will have like this cycle. It can be connected with 6 because we have maybe I will draw a different color. So we have this cycle, and it can be connected with 7 because we have this cycle. So again, we have a contradiction. So we just use the fact that we don't have a 5 cycle, the 3 and 4 cycles here, and prove that there is no way of constructing a Hamiltonian cycle. But you see that I just spend like 10 or maybe 15 minutes to prove that there is no Hamiltonian path in Peterson graph, and Peterson graph is very simple. It consists only on 10 vertices and of 15 edges. So I want to assure you that this problem is actually very hard, and actually it is so-called NP complete problem. So it can be we don't have an algorithm that can find can solve a problem of if there exists a Hamiltonian cycle or not using under the polynomial time. So we can as you see, we cannot have. So we just can try and use the Kalman system. We can use cycles in our graph to prove that our graph is not Hamiltonian. There is like some theorems that have this necessary conditions to be graph to be Hamiltonian. Okay, so for the last example, I don't know if you have time to find something, but I think it has a Hamiltonian path. Let's try to find it. So I think if you have like some task, you can try to just think about how can this Hamiltonian cycle can look, and then if you are trying like 5 to 10 minutes, I can find a Hamiltonian cycle, then we can try to prove that the graph has no Hamiltonian cycle at all. So for this graph, I think we can try to from an vertex and think how we can go through the graph. So I don't know, maybe so. Is it symmetry? So from the beginning, I can just use every edge and then go to the border, and then I just can. So I can just try to construct such graphs that the cycle that I need maybe to go through inner and outer vertex. So, for example, you see that I already used. So I use two adjacent vertices to this guy. So if I need to construct a cycle, so maybe I need to go through this one first, and I need to go through this one, and then through this one. Okay, so it's yeah. So maybe I will try to start with from center. So I need to go like yeah. So maybe I will just go another way. So I try to go through into the graph and it will not have enough, but maybe I will try to. Yes, so I will just. So if I go like here, can again go through this vertex, yes? So how can I modify my cycle to go through this vertex? So maybe I should yeah, so maybe I should go yeah, so the one option here is go here, and okay, so I just go through here, 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 and here. Okay, so I just this three possible again. It's not very easy to find the Hamiltonian cycle, even if graph even if some graph has it has it. So I just would do the following. I just assume that I start from the center, then I go. Maybe I will try it from the beginning. So I started from center, and then I go. So I just use the every edge I can use, and then I go to the border. I can also by the symmetry go to the other border. But then I see that this vertex here have three edges. And so either I need to finish in this vertex, either or I need to use it just now. And I suppose that I use it just now. And then I ended here, and here I have three different possibilities to go through here, and through here. And you see that I just try every possible way. So first I go through here, and then I have a problem because I need to finish either here and here, and I cannot do that because I just need to go there, and then I will finish like maybe I can do this so like this one, yeah. Okay, but otherwise, just I found the cycle, but I also go maybe going through. So I just uh, look at the all possible variations of going through cycle, and then I find the uh, cycle that I need. Okay, so let's talk about some theorems. The two main theorems is the theorem uh, of Ore. It takes that if the number of, so if G is graph on n vertices and n is greater than 3, and for every two vertices degree of one plus degree of other is greater than or equal to n, if v and u are not adjacent, then G is Hamiltonian. And the simple condition for the graph to be Hamiltonian is just need to find the I just forget how this theorem is called. Anyway, it's called Dirac theorem. It's similar theorem. So again, if G is graph on n vertices n greater than 3 and all degrees are greater than it has degree n half of the n or greater, then it is Hamiltonian. And of course, you can see that if we prove the Ore theorem, then we have also the Dirac theorem, because if if all degrees are greater than n over 2, then the sum of two vertices of degree is greater than n. So we have the second theorem. And I just forget talk about this, but of course we can. We suppose that G is simple graph, but of course we can look at the graph. We can look at the directed graph and look at some. So we can just want to find a cycle-oriented cycle in our graph, and it's also called the Hamiltonian graph. But usually we cannot look at the multigraph, so we don't think about the loops and the multiple edges between two vertices, because it have no sense in terms of Hamiltonian graph, because in Hamiltonian graph we need to build a cycle, and how many edges are between two vertices doesn't matter at all. So we just forget about the multigraph, but we can of course look at the directed graphs. But here we assume the graphs are not directed, so First, if we have proof or a theorem, then we prove that's Dirac's theorem. So we just need to prove the first one. If degree of all vertices are greater than n/2, then for each vertex you have like this one. And again, the theorem, so of course the theorem can be stated as that if graph has many edges, then we can find a Hamiltonian path. And not all theorems giving us the Hamiltonian graphs are talking about the number of edges, but of course it is it is easy to construct, so easy to think that if we have like many edges, then our graph somehow have a Hamiltonian cycle. And of course, this theorem is not a criterion, because we have like, if we look at the cycle, for example, through 10 vertices, then it has like 10 edges and 10 vertices, and each vertex has degree 2, and so it doesn't feel that it doesn't meet the conditions of the Euler theorem, but the graph is Hamiltonian. Conditions. The second thing is that it is, so I need maybe give an example where if we, so if we have like lesser conditions, then we cannot have, so it is accurate border of the inequality of the sum of the degrees of adjacent vertices, not adjacent vertices. So can we give an example? Such that the number of vertices is more to 3 or greater, and then the sum of the degree of not adjacent vertices is n or greater, except for one pair, except for example, do we also, so is it true that we don't have a Hamiltonian path here? So I can just give you like 2 or 3 minutes, and then we can discuss it. Actually, you can ask me about the formulation of theorems if you don't understand something. So maybe Sorry, I just disconnected from the iPad. Yeah, I think it's very a simple example. So for example, we start from n equal to 3. What we can uh, imagine is just non-Hamiltonian graph is just the path 3 vertex path, and we see that we have only two non-adjacent vertices, and the sum of the degrees is equal to 2, which less than 3. So for one pair we have this inequality doesn't hold, and so we have no Hamiltonian path. So we can just add like some other vertices and then connect. So for example, we just connect them all between each other. And so again, we will see that this this graph again has no Hamiltonian cycle, and the degrees of so we also can just add, we can connect it like so. This vertex V with one of the vertex has, so this inequality doesn't hold. Okay, so let's prove the theorem. So suppose we have like 3 or more vertices, and for each two vertices that are not connected, we have this inequality that sum of the degrees is more or greater than n. We want to prove that there is a Hamiltonian cycle. There is several different proofs, but all of them are considered so they prove like by contradiction, or we just look at maximal. So consider the maximum path, maximal cycle in our graph, and then we just prove that it contains all the vertices and is Hamiltonian. So is it okay? So maybe again one more question for you: is it true that we have at least one cycle in our graph? Can we prove that we have at least one cycle of in our graph? Okay, so do you hear me? So is the problem is too hard for you? Or do
So
you
yeah, I
understand my
think
question?
there's gonna be a cycle. So.
Yes. Look. Suppose, of course, we have, we have at least one path because we can just take two vertices and they connect each other. Because if so, the degree is very high, so we have at least one edge in our graph. So of course we have path. Suppose we so if we take a maximal path of maximal length, so we have like it can be two or maybe more. So let's look. So let's denote the vertices in here like v1, v2, vm, and so we have like two different uh, two possible variants. So first of all, we can have an edge between v1 and vn. If it is so, then we have a cycle of length m. So I want to prove that if we take a path of maximal length, so this must be cycle of the same length as this path. So if we have v1 and vn, then we have vm. Then we have a cycle of length m, But what if they are not connected to each other? Then we can use the theorem and our condition, and so we can state that if we summarize the degree of v1 plus degree of vm, then it should be greater, less or greater than n or greater. It means that they have so the good uh, again we have two options. First of all, they connect with some vertices outside this path, and of course this is a good variant because we can construct a cycle. And so this but if it is the path of maximal length, then v1 and vm can be connected to any other vertices except from this path. So first, v1 and vn connected only with v2, etc., vm minus 1, because if they was connected to any other vertex, for example here, like w, then we have a path of it is not a path of maximal length because it can construct a path of length m plus 1. So this is not happening here. And of course, and again, vm is not connected with some other vertices because again, it will be not a path of maximal length. So this vertex v1 and vm connected only with the vertices of v2, vm minus 1. So suppose let's consider two different. So first one, I want to prove that we can build a cycle. Okay, and then I will prove that yeah. So this space contains all the vertices. So how to prove that it's from the cycle? Look, if I have this construction, so if v1 is connected with some vertex vk and vm connected with the vertex vk minus 1, then I can build a cycle. I can go from 1 to vk minus 1. Maybe I need to choose a different color here, maybe red. So I go here, then I go here, then I go here, and then I go again here, and I have built a cycle. So if we have edge between v1 and vk and vk minus 1 and vm, then we can build a cycle. Then I will have, how can I prove it? I need to use this inequality here, this condition. So if I denote, if I look at the all, so I look all, so if A is set of the vertices that are connected with Vi, V1, so it's like the Vi such that Vi, V1, Vi is an edge. And if I look at the B, if you take Vi plus 1 such that Vi, Vm is an edge, then A plus B is equal to the number of the degrees. It's just the degrees of our vertices. It is more or greater than n. And so from this, I can get that A plus B is greater than n. And then they intersect with each other. Because they are not greater than n minus 1, then A and B must intersect with each other. They are all subsets of the one, of the two, etc. n minus 1. And so they are intersect with each other. So we have like, does the vertex of number E and number I, sorry, in intersection. So if, and if maybe I will just denote this by K. And so if I have Vk from the A and Vk plus Vk minus 1 connected to the Vm, then we have a cycle. So the idea is fully that I just look at the all vertices that connected to V1, look all the vertices that are connected to the Vk, and since the degrees is great enough, much so the so great enough, then I will find the pair of adjacent vertices. The first one is connected to Vm, and the second one is connected to V1, and then I will have a cycle. Do I understand the proof, or do I need of this, or do I need to repeat something?
So I think when I rewatched the video, maybe it's be more clear.
Okay, so I just again, I just want to prove. So if I have an path of maximal length, then I will have a cycle of maximal length of this same length. And the idea of proof is very straightforward, because so if the first I look at the vertices are there on the edge, on the end of this path, V1 and Vm. Is they connected? We have a cycle. They can be connected from the vertices outside the set of vertices. So they are connected only for the vertices inside. And then I will, if I find the neighbor vertices, the first one is connected to Vm and the second one is connected to V1, then I will have a cycle. I just can go like this. And this inequality gives me that we have, so this degree is too much of V1 plus Vm. Then I will, by the Pidgeot principle, I will always have like this neighbor vertices. Okay, so I just prove that I have a cycle of length n. But if I have a cycle of length m, then if any of the vertices are connected to the vertex outside, then I will have a path of length m plus 1. because uh, because I can start like from this vertex and then go through this one. But I already choose a path of maximal length, so I cannot have any other vertex connected with this cycle. So there is but I'm assured that my graph is connected, because if I look at if I have any adjacent vertices v and double v, then the sum of the degrees is greater than n. And it means that if I look, they have at least one common neighbor. This is u, because the sum of the degrees is greater than n. So I have like at least one neighbor. So the graph is connected. And so it means that there are no other vertices, because I already built a cycle and I can have any other vertices connected to the cycle. And so since my graph is connected, then I just prove that I have a cycle containing all the vertices. So it is built the Hamiltonian graph. Do you understand this last part of the proof?
Yes, sir.
Okay. Okay, so now we have a problem, because we have like 10 minutes left, and so maybe I want I think about giving you another criterion of Hamiltonian graphs, but I think it will take like 15 minutes, and so it's maybe a little bit harder. So I don't think that we need to. Uh, okay. I remember that I will have one additional question for you, and think we'll be finished for today. Okay. So we studied the Hamiltonian graphs and the Euler graphs, the graphs of Euler circuit. And I want to ask you about how they're connected to each other. So my last example will be the following. So suppose G has an Euler circuit. Does it has to be? Does it always will be Hamiltonian cycle? And vice versa. Suppose G has a Hamiltonian cycle. Is it true that G always has an Euler circuit? So is these two notions are connected to each other or no? So maybe I will give you like I think it's not very hard to give you counterexamples. So I can give you like 3 or 4 minutes, and then we can discuss it, and then we'll finish it.
Sir. Sir, can you hear me?
Yeah, of course, yeah, yeah.
Yeah. So I think in a Hamilton cycle we can have we can visit a vertex multiple times. Sorry, in a Euler circuit we can visit a vertex multiple times, but in
Yes,
Hamilton
yes,
we cannot.
yeah, yeah,
Yeah.
yeah. Of course, of course.
Okay.
Sir, so I think G has Hamiltonian cycle does not imply that it has a Euler circuit.
Yeah, and what's the example of this graph?
Uh, so let's assume we have a square
Okay.
with one diagonal, maybe from, yeah.
Okay, so this graph has a Hamiltonian cycle, but this can have another circuit, yes? So this is
Oh, it has? Mm,
yes, he has a of course he has a Hamiltonian cycle like this one, but it
yes, yes,
don't have another circuit because we cannot we do not have a cycle that goes through all the edges.
yes, that's what I'm saying, sir. So it has
Yeah,
an
okay, okay, yeah,
Hamiltonian cycle
yeah, yeah.
does not imply that,
Yeah, of course, yeah. So this is
yeah.
counterexample for this one, and for so maybe you can give a example of where graph has another circuit, but it can have another Hamiltonian cycle. It doesn't have a Hamiltonian cycle.
Sir, maybe Peterson's graph.
Is Peterson's graph Euler has another circuit? I suppose not, because all the vertices are of degree 3, and so it doesn't have another circuit. Because we cannot go through
Yes.
all the edges. We need to.
Uh, I'm sure. So if we have two triangles on top of each other, I think it won't be a Euler circle, but not Hamilton cycle.
Yes, something like this one, yeah?
Yes, sir.
Yeah, of course. So, yeah, surely it's an example because you can have another cycle, but you cannot go Hamiltonian cycle because you can go through this
The center vertex.
Sense, yeah. Okay, yeah. So we did see that there's exactly no connection, but between these two notions. But sometimes we cannot see, because in early circuit the problem is that we can go through each vertex many times, and Hamiltonian cycle we cannot do that, and so it has no strong connection. So maybe in some graphs it's true, but not in. Okay, so I think that's all for today. So next time we will talking about Ramsey graphs a little bit,
Yeah,
and
sir.
yeah.
Yeah. So next class is the last class, right?
Yeah.
Or
I'm sorry that I can't just I have difficult so not my time to see your works about the midterm. I will try to see them this evening. So I will have we have one homework about the Hamiltonian graphs. I think I will just do it today evening or tomorrow evening until the
yes.
16th of December. And for the next part, we don't have no homework, but we'll have we'll have a I don't know how to call it, final exam or second midterm at the 16th of December, where we will have 2 hours, and there must be questions about graphs, about planar graphs, Euler circles, Hamiltonian graphs, and Ramsey graphs, and maybe one task about the combinatorics. And after that, so I think the next time I will make I will make a table where you can see all your marks for all the homeworks and the midterm, and you will see the grades. So I think that 80%, maybe 75% of total number of points will be graded as 10 points, and mark 10 marks, and then I will have linear equation, and so we can see what is your mark. So what will be your mark except for the final homework and the final exam, and so you can prepare it and do it. Okay.
Understood. Thank you.
Sir, so most of the questions in the exam is gonna be about graphs.
Yeah, of course, because it's the second part of the course. So I think there will be I will think about it. So I think it will be four questions about graphs and maybe 1 or 2 about the combinatorics. I will see if there are maybe. So what is not covered by the midterm? So maybe I will give a task about some questions that will not covered by the midterm.
Okay.
But I think it mostly be about graphs. Yeah. Okay.
Okay. Thanks, sir. Goodbye, sir.
Yeah. Goodbye.